All right. Thank you very much for the kind introduction and invitation for the organizers. It's my great pleasure. It's my great honor and pleasure to be here. Also, thanks for all the great lectures. Been learning a lot and have been enjoying this conference so far. Yeah, so today I want to tell you a story about skein trace. I think in the title and abstract, I wrote skein trace and its applications, but I'm not entirely sure if I'll be able to get to the applications, so I apologize if I don't get to that point. But let me start with some motivations. There are at least two motivations. One comes from physics. So we've been learning this week so far about from Andy's lectures about class S theories. And we've learned that we're given a Riemann surface C and a choice of gauge group, which I'll always specialize to gel N. There's some 40 n equals to 2 theory of class S. Denoted S of Riemann surface GLN. And we've also learned that as we go from high energy to low energy, that is, as we choose a point in the Coulomb branch, in the M theory picture, the brane splits and forms some sort of branched n-fold covering over C. And the theory becomes abelian. So it becomes a class S theory based on gauge group GLN instead of GL1 instead of GLN. And here sigma is a spectral curve, which is an n-fold branch cover over C. So as we've been seeing throughout this week, the class S theory is an interesting theory, but one of the aspects that I'm interested in is its line defects. And the class S theory carries the category of line defects. So let me denote by this curly L to be category. It's a monodal category of line defects in that theory, and likewise for the theory in the IR. Then, like one of the physics predictions is that as we flow from high energy to low energy, there should be a corresponding functor between these categories. So, oh, sorry, but before that, the first physics prediction is that this monodal category, after decategorification, that is after we take the Grothendieck group, it becomes an associative algebra known as the skein algebra, which I'll define later in this talk. So skein algebra based on GLN. And yeah, second, there should be a what I might call a UV-IR functor so it should be some monoidal functor from the category of UV line defects to the category of IR line defects. And continuing and in particular, by taking the Grothendieck group, there should be a corresponding algebra morphism from the algebra line defects in UV to that of the IR. That is an algebra morphism from the GLN skein algebra of C to the GL1 skein algebra of the spectral curve. And this is in fact what was studied by Andy, Neitzke, and Fei Yan, I think from 2020 or so, where they've constructed such a map for some class of C and sigma when n is equal to 2, and in some cases n is equal to 3. And yeah, so we would like to understand how these line defects behave as we flow from UV to IR. That's one of the motivations. There's a second motivation. Let's say from mathematics. Let log n of C to be the moduli space of rank n local systems on C. And I'm not going to make a distinction between Betty versus Turaev, so I'll just think of it as the moduli space of GLN flat connections. And in the work of Fock and Goncharov, they've showed that this moduli space has an interesting coordinate system, so-called cluster coordinates. And this is closely related to what Andy was talking about in his lecture earlier today. And roughly speaking, saying that it admits a cluster of coordinates means has some coordinate charts where each chart is some algebraic torus. Say C star to some power, so that its ring of functions is some Laurent polynomial ring, and the coordinate transformations are given by so-called cluster transformations. Very specific kinds of birational maps between these algebraic torus. But what's important for us is that these cluster coordinates were in the work of Gaiotto, more Neitzke, these cluster coordinates were identified with the rank 1 local systems on the spectral curve. They can be identified with rank 1 local systems on the spectral curve. Well, let me also put U. So U, the choice is a point in Coulomb branch. And so recall from Andy's lecture that a Coulomb branch admits some sort of like chamber decomposition. And so within each chamber, these coordinates look locally constant. And as we cross the walls of this Walling chamber structure, the way these coordinates transform is exactly by the cluster transformation. And this story admits quantization. Yes, yes. Arbitrary rank. Yeah, I think Chekhov and Fock might have done rank 1 or some earlier work, and then Fock and Goncharov. Yeah. Any more questions so far? So what Fock and Goncharov showed on top of that is that any cluster varieties can be quantized. They admit a natural quantization. And roughly speaking, what that means is instead of having algebraic torus for each chart, we'll assign some quantum torus. That is, instead of having Laurent polynomials as coordinate ring, we'll have Laurent polynomials in q-commuting variables as quantized coordinate ring in each chart. So we'll have quantum torus in the quantized setting. And the way the coordinate transformation works in the quantum setting is by what's called the quantum cluster transformation, which is conjugation by quantum dialog. Yeah, and I'll say a bit more about quantum dialogues later. On the other hand, there is another quantization which, as shown by Turaev, any moduli local systems can be quantized to the skein algebra, the exact same skein algebra that I was talking about earlier. So, like if we interpret these story appropriately for the two quantizations to agree, there should be maps from the GLN skein algebra of C to GL1 skein algebra of the spectral curves. And moreover, as we vary the spectral curve and as we pass through a wall, the way these maps transform should be exactly via quantum cluster transformation, that is, by conjugation by a quantum dilogarithm. Such maps were indeed constructed. Bonahon and Wong. Think around 2010. And yeah, and the way they constructed such a map is algebraic, meaning they tell us how like each element of the skein gets mapped to and to particular element of the quantum torus, and then check that it's well defined, behaves well under coordinate transformation, etc. Oh yeah, and they call their map quantum trace. And yeah, since their construction was algebraic, it doesn't seem I mean, it doesn't make it clear why there should be such a map a priori. Yes, GL1 skein algebras are quantum. Yeah, there are some Q commuting. You know, they're generated by Q commuting elements. True. Also, I'm kind of sweeping things under the rug because like they work with SL2, but yeah, they can be compared directly. Yeah. Yeah. Why should such maps? Priori. Well, I guess physics tells us one answer. That physics predicts. But the goal is to give a geometric reason why such a map should exist. Yeah. So what I'm going to tell you today is a generalization of this quantum trace to the Humphreys setup, hence the name skein trace in the title. So let me now start defining the main objects. Yeah, and in fact, even though so far I've only been talking about surfaces, which is the most relevant for the class S theories, can be generalized to arbitrary three manifolds, and that's where we'll be working at. So let M be an oriented three manifold. R is going to be our base ring, which can take to be Laurent polynomials in two variables, A and Z. If you're more familiar with Q variable, Z is always Q minus Q inverse. Then the Humphrey skein module Since I'll be almost exclusively work with Humphrey skein modules, I'll just drop the adjective Humphrey most of the times. But so whenever I say skein modules, it means Humphrey skein. The Humphrey skein module denoted as K of M is the following R module. So it is the R span or R linear combinations of all framed oriented links in M. Yeah, so a link is just a smooth embedding of some number of copies of S1 to M. And we say that they're framed if they carry some normal vector fields along those circles. And modulo isotopies and skein relations. There are some linear relations that I'll write down in the next board. So there are 3 skein relations. I'll first write down the relations in